Okay, welcome back. Happy Thursday. The week is almost over, so I hope that you guys are happy. So our goal today is to come back to system initialization and essentially finish creating the real kernel page table. And the idea here, why it is important, is because this code, which we're going to discuss today, is essentially the same code you can write when you will be doing your homework, which will assign, hopefully today as usual. So just, I don't know, like what's the best combination? I was trying to switch with this slide. Okay, so anyway, so let me quickly remind what we were doing last time. So last time we constructed a memory allocator, a very simple one, which was keeping track of physical pages in a linked list as a linked list, right? So a linked list allows us O1 allocation. So essentially just a one constant. You just get a pointer to the first available element on the list from a global variable, and you assign this global pointer to the pointer pointed by the element of the list, right? So you just pop something from the top, from the start of the list, right? It's very easy, and remember the trick which we did. So we said, okay, since we really this list itself lives within the pages, right? So it's a little bit of a hockey design choice, right? So there are multiple design choices you can make, and this choice is somewhat suboptimal, but we can discuss it a little bit later. One other choice would be to just have some global variable, some array, for example, of, let's say, some number of elements. And in that array, you can keep track of which elements are available and which are not, right? Then you don't need to have all the memory of those pages mapped in the kernel, right? Is this argument make sense to you? Because this is kind of important and it will come back later. Is that clear? Like, I'm sure like it's clear to everyone who is in the room. I'm pretty sure that people who are paying a little bit less attention it might be confusing, but okay. So there will be a question about it later in the class. So just make sure that you understand what we're doing here. And we said, okay, since we need those pages to be mapped, since we have to access the elements of the list, we said, okay, we need to allocate the list inside the memory, which is already mapped, right? And we said, okay, since we already have 4 megabytes of memory mapped, there is likely some memory which is available from the very end of the kernel to the end of that 4th megabyte, right? And we said, okay, those pages will be the pages which we'll be tracking, right? And there is this implicit assumption or design choice which we made. We said, okay, our real goal is to track available physical resources. So if you have this physical memory, and you say the kernel is sitting here, and this is the end. This is where the tags, data, and BSS sections of the kernel end. We say, let's round it up to the next available page, and then we will start tracking those pages, right? And we say, look, this is a physical page with some physical page number. I don't know, let's say 15 for the sake of it. Maybe it's not 15, most likely it's not 15. This page is 16, right? Like everything starts from 0 here because it's physical memory, right? And we say, look, we're going to track this. Really, the resource which we're allocating is really this page, right? The very first time we get kalloc, we'll get, let's assume, this page 15. I actually don't remember which way the list is initialized. Maybe the very first page we will get is actually this one. Let's say page X here, right? I don't remember. Maybe it's backwards. I don't remember the order, right? Because most likely it's backward, because remember, the way we said we initialize the list, we say this is the region of memory, and we will be walking this region starting from the beginning to the end and adding elements to the list, right? So which means that this page 15 will be added to the list first, and then 16, and then 17, and so on, right? So this page X will be added last and will be at the very top of the list, right? So that makes sense, right? So this is how these data structures which we chose to implement at work, right? But an interesting fact, since every time you need to put something on a list, you need to access a piece of this page, right? So it has to be mapped. And so the way we mapped it is we didn't map it like at address 0, although it is mapped there right now with our entry page directory, right? So this boot time page table, since our plan is to get rid of it, the way we track those pages is by looking at this. We add this 2 gigabytes for essentially the number 2 gigabytes, which is in hex. Sorry, in hex is 8000, 3 zeros here and 4 zeros here, which is exactly the beginning of the second gigabyte. And this is where the kernel is sitting, right? And this page 15 will be frame number, I don't know what it is. Like, obviously, it will be this number, OX0. This 0 will turn into 15, which is what? Which is F, right? This is exact page number. Just eyeballing it, but those numbers make sense. So this arithmetic which I did, does it make sense to you? Any questions about it? How we came to this number, 8000F, right? The logic here is that I'm saying that in hex 15 is F, and since we're adding this shift, and since it's a page number, so this is an offset within a page, right? Because remember, it's 12 bits and each 0 represents 4 bits. So 3 zeros is exactly 12 bits. So this part of this number is actually a virtual page number, right? So this is why I wrote it 800030 zeros. And instead of this 0, because we're adding 15, I added F, right? So this, just again, like this number, so at some point you need to get a feeling of how it works. So like it just later on when you debug a problem, you say, look, I see this magical address. For example, I'm trying to access an address in the kernel, and I clearly don't see this 8 in front of it. That means that you're doing something wrong, right? So you have to be in that neighborhood. Okay, so we remember this, right? And now we say, okay, our plan is to construct a page table. So we have a page, we have an allocator. Every time we do a kalloc, it returns a virtual address. So in our case, this address V is exactly this page, right? This is like, and we say, now we can construct a page table, because the very first thing which we're gonna do when we construct a page table is we will allocate a page for a page table directory, right? For the root of the page table tree. Agree? Okay, so let's do it. So let's quickly go through this and first understand the high-level story, and then take a look at the source code to understand how one might write this code, right? And it's actually not that hard, but again, the first time you read it, it's a little challenging, right? So we're specifically looking at this function, kv malloc, right? So the way to read this name is kernel virtual memory alloc, right? So KVM stands for KVM, right? So kernel virtual memory, right? Okay, so the logic is the following, right? And we kind of briefly discussed this last time, but let me go over it again. So we say we want to map the all available memory up to this 234 megabytes, which is defined at this fizstop constant, because we don't want to really care about how much physical memory our machine has, because it requires us to talk to BIOS. It's actually not that hard, because if we're running on top of Grub, a bootloader, actually, yeah, I take it back. It's actually is challenging. When you're running on top of Grub, when you're building a real operating system for profit, for example, you'll say, I'm going to boot on top of a bootloader, and there is a specific protocol which bootloader will implement, and it will pass you available physical memory. So you don't really have to implement logic of talking to the BIOS. But we're running on top of our own bootloader, right? So there's tiny 512 bytes. Nothing has happened. So we never queried the BIOS. We just disregarded it completely. We just said, okay, disable interrupts. We never want to hear back from you. And so we don't really know how much physical memory is, right? So we just optimistically assume that this 234 megabytes are available, right? And I mean, like if it comes that we're running on a smaller system, we just change this constant and we will be just fine, right? For educational purposes, this is fine. We say, okay, like we know that we want to map this memory, definitely this one, up to fizstop, but it turns out that we are clever and we say we're going to map it as 3 different regions here. So first region, which is the IO space, which allows you to communicate with device drivers, we're going to map with read and write flags. Then we're going to map the read-only portion of the kernel and the data section with read-only flags. And this will allow us to catch bugs early. The moment you try to write a kernel, you will crash. And you crash early, so it will be like easier to understand what's going on, right? Specifically, the instruction which touches memory will be under the instruction pointer register. Then we're going to map this region as read-write. The kernel read-write portion of the data section, and everything about the end symbol, which will be our heap, this available physical pages. Right now we are like from the end, let's imagine somewhere here there is an end symbol, and we went up to 4 megabyte and like cut it in pages, and these pages are already available for allocation. They are tracked by our allocator. And the rest of it, we will just, after we construct the first page table, we're going to add those other pages up to FizzTop to the list of 3 pages, right? So this way we will be able to operate with all available physical memory, right? And run the system like that. Agree? And again, so this will be read-write. These pages will be our like a pool of pages which we're going to use for constructing processes, right? And so that's useful. And there is another quirk here, this like IO region, which sits on top of the physical address space. It's not mapped by real physical memory. So you may have a machine which has only 16 megabytes of memory, and then still this region is valid. So if you do a write, it's just a combination of memory controller and a PCI controller, which allows you to communicate with external devices, will convert this right into this IO space to some magical packet, which will go to some device on a PCI bus. And if you like don't follow a specific protocol, like for example, device is not present, then you do a write, and most likely you will get something what is called a machine check exception. So essentially, the machine will tell you, okay, I don't really know what to do. You're doing something wrong. We're gonna machine check exception. I think it's an interrupt, so you can actually process it and recover, but in our case, we most likely will say, okay, we don't really know what's going on at this point, panic, and you're going to reboot, right? Okay, cool. So that's the plan. 4 regions, right? And our outline starts like this. We're going to map a region of virtual memory starting from the 2nd gigabyte. And we're going to iterate it page by page in the increments of 4 kilobytes, right? But first, we'll allocate the page table directory. And we will be allocating leaves in the page table as we need them, right? So obviously we'll allocate a leaf immediately because we're not going to have the leaf. But then since one leaf allows us to map 4 megabytes of consecutive virtual memory, every time we're going to be crossing a 4 megabyte boundary, we're going to allocate a new leaf, right? And this is how you can eyeball how many leaves we will need, right? Because you can divide this FizzTop divide by 4 megabytes, you will see how many leaves we need, right? Agree? Yeah.
I had a question.
Yeah, go ahead.
So for page table, is there a rule to prevent you from modifying page table?
Sorry, can you say it again?
Can you not modify a page table while it's in use, or is that perfectly?
Can you modify the page table?
Well, while you're using it.
Yeah, absolutely, it's legal. I mean, you need to do that, right? Because imagine someone says, okay, please, you invoke something like an mmap system call on Linux or on x86, it will be sbrk set bracket, saying, okay, give me more pages, because you try to do a malloc. A local in-process allocator says, I ran out of local memory, please give me a page, or give me 10 pages. At this point, you drop into the kernel, and you say, okay, I need to add those pages to the page table, and you do modify the page table. Next time you access this virtual address, you will go through this translation and it will be valid, right? So the hardware will react properly. There is additional detail here, which is kind of important. Remember, I was talking about this TLB. So TLB is a cache, translation leukocyte buffer, is a cache which on the CPU caches translations from virtual to physical addresses, right? So for frequently accessed addresses, you don't really have to walk the page table. I mean, when I say you, I mean hardware, right? And there is a little bit of a problem here, because this cache doesn't really know that you modified something in physical memory in the page table. it will happily read a new translation and will cache it. However, if you remove a page here, this is where you get in trouble because the translation is still cached. And at this point, you need to invalidate the cache, making sure that, okay, I removed the page. Maybe you say, instead of SBRK moving forward, you had a bunch of freed memory, and you say, I'm going to release the memory back to the kernel. So you SBRK back to the, like, to a negative number, so essentially like deallocating space in the other space, or unmap the memory on Linux. At this point, the kernel has to say, I see that this page will no longer be mapped by the page table, so I will like signal to the TLB to make sure that this translation, the cache translation, is no longer valid. So there is a specific instruction. Back in the days, it was very expensive operation. So initially hardware didn't have a like support for invalidating individual translations. And essentially you have to clear the entire TLB, which is painful because you have to reread all the translations again. It's a huge performance penalty. Today, there's an instruction which says, okay, please invalidate only this one entry. And this is what you have to do as an operating system designer. We'll see how x86 handles it when it handles SBRK, how it unmaps the page. Again, like tiny detail, but kind of important. So good question. Everyone is on board with this logic? Good, okay. And then we will be like filling page table entries essentially with proper physical addresses, right? So essentially, if you want to map a specific address, you just update an entry in a page table, right? Okay, let's take a look at how it might work. So imagine this is your address space, right? Right now you have this entry time page table. These two regions are mapped, right? We're going to be using this region, top, this. In fact, we'll never use this region again, right? So we just, the entry is here. We didn't invalidate it, although we could. The moment we did that long jump into the kernel, we could have invalidated this first entry in this entry page directory here, right? What we're going to do is we'll do the following. We'll take a virtual address, which will point exactly at this boundary of 2 gigabytes, which is address 0x8000 and 4 zeros here, right? And we say, okay, I will try to map it. So since I don't have page table directory yet, maybe we'll allocate it upfront, right? So we will allocate a new page table directory, right? The hardware doesn't yet know about this page table directory. It's just a page in memory, right? It's sitting somewhere here in physical memory, like right after this, sorry. As I was saying, since we're going backwards, most likely in that list, this is the page which we will get. And it sits as in terms of virtual addresses, it sits right here. This will become your page table directory, right? Virtual pointer. You say, okay, sure. Then what you do, you take this address, virtual address, you split it into 10 top bits, 10 middle bits, and there's 12 bits, which you don't care about. You take, because this is how the translation works, right? So you say, I will take these top bits, which we call page directory index. X stands for index. That's notation from x86. And you say, okay, what is this entry? I'm kind of claiming that it will be entry 512, right? So this is this entry in the middle of a page table, right? Exactly in the middle, right? Because imagine each leaf covers 4 megabytes. So you start, this entry 0 would allow us to cover these 4 megabytes, right? Then the next one will cover the next, and so on, right? Entry 512 will be exactly in the middle of this address space, right? We say, sure, that sounds good, let's do it. But you say, look, but I don't really have a pointer here, right? Because this entry is invalid. At this point, you say, I really need to allocate the page table. I call it level 2. Maybe my notation is not ideal, but anyway. So it's page table pointer, right, from our allocator. And we will get this page. Again, if I want to be very concrete, I'm pretty sure that it's the second page which sits here, which physically is right here. This is the page. This is the physical address of this page tab. Let's say physical. And this is the virtual address. So this is where it is, right? And you say, okay, since I want to connect these leaves, so I will write here the physical page number of this page, right? So I will write page tab PG page table. What is, oh, page table physical address, but I will like take a physical page number, right? So only the top 20 bits, right? Agree with this? So this will establish this pointer, right? No? Someone is confused? Okay, go ahead.
Alloc will return virtual page number, right?
Alloc will return a virtual address, right?
And we need to convert from that to physical and store that in byte or internet.
Correct. And how do we convert from this virtual address to a physical address?
If we add a place kernel base, we have macro button.
Correct. So remember that this is a magic here. Like we said, this is how we construct this address space, and we know about it. So this is plus 2 GBs, right? So if you want to convert this virtual address into this physical address, you just subtract 2 GBs, right? And there will be a macro which is called V2P, which just internally just subtracts 2 gigabytes, right? Again, this is how we construct it, and that's why this macro works, right? Clear? Or at least, yeah. Okay, cool. So then we have this page table level 2, and we're kind of good to go. We say, okay, this virtual address, which we will take this middle 10 bits, right? And I claim that we'll land on entry 0 because it's at the very beginning of this region, right? So into this entry, what are we gonna write? Physical page number of which page?
We need to allocate one more.
No. Why do we need to allocate a page? We're mapping a page, right? We are mapping a very specific page. Which one? Page 0, exactly. So we are mapping this virtual address into this physical address, right? And this physical address is this page. Agree? Because the whole point of this is to map. We don't want to allocate. We just want to map. It's kind of like saying assigning seats. You know, you have physical seats. Students are coming, and we say, okay, this seat will must be assigned to a student. I don't know. This may be not the best analogy, but you can. A better analogy is to think of a co-working space in which you have offices, which every day you might allocate to new people. Those are your physical resources, right? And an organization comes, like, you know, University of Utah says, okay, we're going to use 10 rooms today. And you say, look, here's a mapping. Room number, I don't know, 10 is your room number 0, for example, right? So that's the mapping between virtual resource, which University of Utah is occupying today. Room numbers 10, for example, right? Question?
Yeah, so we're mapping 2 levels of page table directories, like page level 3 and page table level 2.
Mm-hmm.
Doesn't that set us up for doing 4 kilobyte?
Does it what?
Don't we do that to 4 kilobyte pages rather than 4 megabyte pages?
Yeah, so pages are 4 kilobytes. So this page which we're mapping, this one is a 4 kilobyte page, and this one is also 4 kilobyte.
Okay, so are we going to need to fill that our page table up to everything that we mapped so far?
No, like this is the very first mapping which I'm doing. So the mapping on this virtual address, which is exactly address x80000000 to physical address 0, right?
Yeah, I guess my question is just why did we do a page table level 2 when we could have just set a 4 megabyte page?
Why haven't we used 4 megabyte pages? Our only reason, and it's possible, is only a design choice. And design choice is the following. You say, my programs which I'm going to run here are truly tiny. This WC, cat, shell, they fit in a couple of pages, often in one page. I don't want to waste 4 megabytes of physical memory just to run a cat, because then I will be limited by the number of cats I can run, right, on my system. And you say, okay, I can optimize my resources in such a manner that I can run more instances of cat. And if they need more memory in the heap, I will be dynamically allocating this memory for those programs, right? But my unit, my granularity of minimal allocation will be 4 kilobytes. So in order to start a process, roughly speaking, I will waste at least 1 page. In practice, you will waste more, right? And we will count those pages later, but that's the logic. In a different scenario, you say, look, I know that I'm going to run a giant database. I will then can switch to 4 megabyte pages. And this is what Linux is doing underneath. Got the first answer to this question is clear, right? Okay, second follow-up.
So that means, so page tables can only either be 4 megabyte map or 4 kilobyte map. They can't be hybrid.
They can.
Okay.
So, and remember this bit. I don't know how it was back in the days, but I know for sure they can be hybrid on 64-bit machines. I'm pretty sure they can work. They can be hybrid on 32-bit machines as well. Remember, there is this bit here in a page table directory, which tells you whether this is a 4 megabyte page or a 4 kilobyte page, or this entry. And if it's a 4 kilobyte page, you then go and look, the hardware goes and looks at the leaf. And if it's a 4 megabyte page, it just interprets this address as an address of the page. And it can be hybrid. And this is very clever because you say, look, I'm loading something like my MySQL DB. It's not giant. It's just whatever, maybe like 4 megabytes, like let's say like 3.5 megabytes. You say, maybe I will allocate 4 kilobyte pages or maybe 2 megabyte pages on 64-bit machine. And then you say, this is fine. I'm not going to waste a lot of memory. But then you say, but I know that the database which I'm going to be loading in memory is giant, like gigabytes. And at this point, you start allocating gigabyte chunks of the heap. And so this way you kind of combine both worlds, like fine grain for text and data, because it's typically tiny. If you're doing a text data section, which is of one gigabyte, you immediately get fired. But so that's why you move this data in a heap, right? All good?
You get like PD and BD are allocated in the kernel physical memory, right? But here we are already starting at 0 in physical memory, right? So those 2 pages are already allocated for PD and BD, right?
Those 2 pages are allocated, right?
To come from physical.
Yeah, this, like I will draw them for you. This is like my page, which is page table directory. And this is my page for my page table level 2. And they physically sit here. They're part of that region which we added to the allocator. They're not part of the, like, okay. Let's just look at those pages. They're right there. They are not running away, and they were empty. Before we allocated them, they were unused. So it was okay to grab them from the pool of available physical pages and use them for something, right? I don't want to tag them as like kernel or user. They were free, right? And it happens to be that our kernel will map all available physical memory, because this is how we map the memory, right? Well, maybe it will become clear a little bit later, but ask your question again with this knowledge. So what confuses you here?
Because we are building the TTE, right? So there, in that entry, we're adding the physical addresses, right? So which is starting from 0 to, let's say we go to 4 MB.
Right.
So those 2 pages, those 2 entries will also be there in TTE, right?
Correct. We will map them because we'll be able to use them. In fact, we will map everything. We will map this entire region from 0 to the fifth stop. Oh, okay, maybe my fifth stop ends here. This is fifth stop. Right? Because in order to access a page, it has to be mapped, right? And then we will map this IO space just for the sake of having a device driver, which might use this IO space. But it's kind of like, it's more of an accounting thing. So you say, look, I have this memory. If I want to access this memory, I need to have it on a page table. You definitely want to map pages which the kernel executes and accesses, right? But you also map these pages, like additional pages, to make sure that later on, it will become clear why we access those pages and why we have them mapped. It's not strictly necessary to have them mapped. But again, we're making this design choice, right? But the thing which you have to remember is, if you have a physical page and you want to access it, like do a write or read from that page, it has to be mapped by the page table, right? If you don't want to access it, you don't have to map it. And maybe you will map it by a different page table, which user will be able to access. And it's totally fine, but you just need to keep track of what is mapped, what isn't mapped. And the most important, you want to keep track of what is available and what is not available, right? What is free still, right? Okay, any other question? This is a good point to ask questions, because if you understand the layout of this address space, everything is a lot more easier later.
I want to make sure I understand this. So we map every 4 kilobyte page, whether it's in use or free, and we mark it as in use or free. That way, if we want to use the page, we have reference to it. Basic idea.
Not quite. So let me just move forward maybe to just our goal is to have a page table which will allow us to access all available physical memory, which means that we will start and we'll go page by page. We'll skip this region and we'll go page by page here, right? The way we will map it is to that address 0 goes to address 2 GBs, right? So this is 2 GBs. So we're going page by page. We take this virtual address and map it to this physical page. Take this virtual address and map it to this page. At this point, we are not tracking which pages are available, which are not available. We just simply are mapping. The mechanism which tracks what is available and what is not available is a linked list, which right now tracks just this tiny region of green memory. Those are two different mechanisms. One is a linked list, and one is just a mapping. But and this is what we're constructing, this mapping right now.
Are we able to use the linked list because we did the mapping?
We can access the linked list. We can access those pages here just because they are mapped right by this page table. And we want to continue using it. That's why we also will map those pages on our new page table here as well, right? So because we say, look, the moment we switch to this new page table, the moment we set the CR3 control register 3 to point to this new page table, everything should work. We don't want to break here, right? So that's why we carefully construct the mapping to make sure that everything what used to be available continues to be available, but there will be a little bit more. Like, for example, if right now only this memory, the first 4 megabytes like probably it ends up to the kernel because, okay, let me just erase. So right now we have mapping for something like here. This is the end symbol of the kernel, and from end to 4 megabytes, right? So let's assume this is 4 megabyte mark. Right now we have only this mapped, but we want to map more. We want to map everything up to FISTOP and this IO space region as well, making sure that we can access all of it on this page table. Right? That's the goal. I mean, I agree, it's a little unusual because there is a chicken and egg a little bit here. But later on, it's very important to understand what we're doing here, because we will come back later when we start constructing processes and stuff. And like that's part of this kernel design. So you have to keep those mappings kind of in your head to understand what's going on.
Just to clarify, is the thing that marks whether they're mapped or not in the page table, or is it stored in the address?
It's in a page table, because the way, imagine you have some random address V, right? You say, this is how the hardware interprets what physical address it has to access. It doesn't know yet up front, right? So it says, okay, I'll take a look at this address. I will split it into this 10 bits, 10 bits, and 12 bits. And I will take this 10 bits and we'll land on this entry, right, in the page table. Let's say it's 5, for example, right? This is entry number 5. I will check that this present bit is set. If it's set, then I will follow this pointer, go to the next level of translation. We'll take these 10 bits, imagine it's 7. We'll go land on entry 7, and we'll interpret this address as an actual physical address of a page, and then use this 12 bits as an offset within a page. If this is also present, so this one is present and this one is present, then I treat the translation as valid, and I will issue the memory reader write to this address. And so if it's suddenly not mapped, then it's a page fault, right? The hardware is kind of like very, very dumb, so it just blindly follows the protocol. Does it help?
Yeah, and then if any of those weren't present, you would allocate them then for the free first two tables, or if that's still good for all?
Like the hardware will react as a page fault. I will explain how interrupts work and how page fault works. Although x86 doesn't implement page fault, but hypothetically, we can implement a page fault saying, okay, I see that you're trying to access this address. At this point, we might check some metadata and decide that this access might be either legal or illegal. If it's illegal, we will kill the process, for example. If it's legal, maybe we took this page and swapped it out to disk. We will allocate a new physical page, bring the data from disk into this physical page, and correct the mapping, and return from the page fault, allowing the user code to continue running, and we'll retry the translation. And hopefully at this point, the translation will be valid. Does it make sense? Okay, this is how it works. But the hardware just blindly walks the page table, says, okay, is it legal? Is there translation present? If yes, we will access the address. If not, page fault. But you have a chance, as an operating system kernel, you have a chance to correct the page fault. And it's your choice whether you want to correct or you want to construct everything upfront and never correct anything. And it's like kernels do both. Any other questions? All good? Okay, so finally we say, like, we want to populate in this red entry, we want to write something. And we said we want to write this physical address, which happens to be 0, but like in a more generic case, you say, well, we'll write this P as a physical page number. So essentially truncating the lowest 12 bits. And we will OR it with the flags. This is my OR operation, right? So essentially, if I want some flags, if I want something like read, write, and probably at least present, right? So here I want to have P as well. Then I will put those flags, I will OR them, and I will physically write into this location, right? And then the mapping is done. At this point, I'm done. I am okay to move to the next page. So essentially saying P plus 4 here, V plus 4 here, and I will land on this entry, right? Since these yellow entries are already present, I don't have to allocate page table directory. I don't have to allocate page table level 2. I will just simply update this entry. Sorry, I don't have a slide for that, but just writing like P plus 4 K, or like masking it with or ORing it with the mode, with the flags which I want to put there, right? And so on. I will be going page by page by page. At some point, I will cross this 4 megabyte mark. I will land on a page which is here. I will, at this point, say I will move to the next entry in this page table. It will be 513. I will allocate another leaf, and I will continue populating the entries in the leaf, right? Agree? Okay, so I know it's a little unusual. It's part of your homework to construct a page table like that, right? Which is not yet assigned, but will be assigned, right? Okay, we understand the high-level picture. Everyone is clear on that. Let's stop here again. If you have a question, let's ask it, because we'll start looking at the source code now.
Is this some on operating system script, or do they do things smarter than that?
It's pretty close. I mean, there is a multitude of opportunities and optimizations. So, but if you understand what x86 is doing, you kind of have a good baseline. You can then deviate from it and understand, okay, Linux might do something different, but it's pretty much the same. So it's a decent way to do something. So it's not that far away from reality. Anything else?
So is 4 megabytes the largest size at the page table, like the amount of pages essentially, and that's why you selected next week?
Right, because I mean, this is how the math works. One pointer here points to a leaf, right? Leaf has 1024 entries. Each entry allows you to map a page. Each page is 4096 bytes, right? If you do the multiplication, you will end up with 4 megabytes. That's the only thing which I mean here, just this math. Anything else? Good. Okay, let's take a look at the source code. I mean, nothing surprised, but the syntax of the notation might be slightly different from what you're used to. Like, names will be very short. Again, the goal was to fit the source code so you can print it out on an actual, two-column text, so you can scroll through it and like read it in an actual like physical PDF, right? And in general, I mean, the style is just a style. You can pick anything, right? Those guys who wrote this kernel pick a decent style. Okay, so we're descending into this kvm alloc function, and we say, okay, we will call this setup kvm. So essentially, this function will essentially return us a kernel page directory, that root which we can allocate internally. And what we're going to do is we immediately will switch the hardware. So the switch kernel virtual memory will switch to a new, like to this new page table, right? So essentially, we'll set CR3 to point to this page table. But let's first take a look at how this setup kvm is implemented. Again, the beauty here, 4 lines of code. Like, look, lines are consecutive. I didn't erase anything in this specific example. So again, on purpose, to make sure that you say, okay, it's very concrete. So if you read this source code, you understand that this is how it's done. There is no magical black boxes. I'm skipping lines rarely here in this kernel. So something what is ultimately irrelevant and like very, very low level, then we skip it. But otherwise, just easy, like everything is there. So I'll skip a little bit here, the 3 dots. Okay, as I was saying, setup kvm, this is the function. We declare this as a pointer to the page table directory, like, right? We say, okay, before even starting, we will allocate a page table directory from our kernel memory allocator. We obviously might fail. So then we return 0, and probably at this point we happily crash, but we don't even check the return values in the boot code, just optimistically hoping that like, memory is there. We set this page to zeros, just to make sure that all entries are invalid, right, originally. And start doing our business here. So virtual address, physical address, we already allocate the page table directory. That's what we've done, right? We say, now we will enter this loop. Remember, I was saying that we're going to move page by page by page. But since I said we have this a little bit of regions, like 4 different regions. One will be mapped read-write, the next one read-only, the next one read-write, and the upper region in the bias region here will be mapped read-write. We will keep them as a kernel map array. This kernel map array just describes those regions, like beginning, start address, end address, virtual addresses, and physical addresses as well. And so we say, look, for all these entries in this kernel map, right, we're going to map the pages, like I said, like do this mapping into this page table, starting from the region's virtual address, going to the region's, this is the region virtual address start, and this is the region physical address start, right? We're just subtracting physical address and from physical, oh, sorry, this is the size, right? And we will take the physical region start. So this was virtual start. This is physical start. And these permissions are the flags, kind of like read-write or maybe read-only, stuff like that, right? So at a high level, we just say, okay, invoke this function, it will map a region. And this kernel map just describes the region itself, right? So not super hard. So if I would ask you to do that, especially in your favorite language, not like C, but maybe C++ or C# or whatever you guys know, Java, you would say, okay, that's decent. Like I have an array of data structures, they describe regions. I will just walk through the array and map everything, right? Okay, not too bad. Let's quickly take a look at this array. Again, the array itself just has 4 elements which map those things at specific, this ends here, and so 1, 2, 3, and 4. And this is how we declare it. So essentially, this is definition of this data structure. It has a virtual address start, has a physical address start, has physical end, which allows you to compute the size like we did just a second ago, and the permission. So very minimal. And again, full definition is on the screen. And you say this array, this is how you initialize an array. You say like, I don't know the size, but like the compiler will compute it, right? So this first IO space region, which is here, you say the virtual will be kern base, which is this OX, sorry, which way I did go, probably forward, X8000, 0.0.0.0.0.0, which is like 2 gigabytes, right? Virtual start, that's where we want to map it. Physical 0, because it starts at this physical address 0. We go up to this constant, which is extended memory. So this is the physical end, which is the first megabyte. And the permissions are write permissions, right? The next region is kernel link. This is like where the kernel is linked. It's exactly 1 megabyte. We translate it from virtual to physical. So essentially, it's really 2 gigabytes plus 1 megabyte virtual. This is where we link the kernel. Remember, we linked it to run at this address. All the addresses in the kernel will be of this form. So it's essentially x80100000. This stands for 1 megabyte, and this stands for 2 gigabytes. So it's exactly 2 gigabytes plus 1 megabyte. And you say, look, you go up to kernel data because this region is read-only. Our permissions are 0. We don't want to write into that region, and so on, right? Starting from data, this is where the data section starts. So it's roughly this address, right? This is where data. You say from data, virtual to physical of data, and we're mapping up to physstop, which is this constant, right? And permissions are right. And the last region is this dev space. We're mapping 1-to-1. That's why this comes twice, right? So there's no 2 gigabyte shift. It just mapped straight down. So because that's how we want it. What is this? This is a trick. This is to specify the end. The end is this address, but we want to map it. So it's +1. So that's why it's 0. So a little bit of trickery here. And the permissions are right. Again, the details are not super important. But again, I just want you to have the feeling. I mean, what I'm trying to teach, which is a little ironic, confidence. Confidence is that when you read the line of the kernel code, you, with a high probability, let's say 90%, understand what it does, right? It's a little tricky because you can teach this course and say, okay, this works this way and this works this way, but you never show any real code. And then maybe you, at some point, you land on a job, maybe some embedded company, which builds, I don't know, a TV top box, or what is it called? What's this? Like whatever. Set-top box, right? Like which you program and someone gives you an operating system. Today it's most likely Linux, but maybe you're unlucky and you got into some company which uses something else, home build operating system, and they tell you, okay, like please do something with a page table. And then you kind of screwed because you say, look, I have to read the source code and understand suddenly how everything is mapped. And your choices are either like going and like asking people like every time what's going on in that kernel, or you maybe have a chance to read it and understand it. And it's, I mean, it happens to the kernel. Maybe you're programming Apache Web Server, you will have to read the source code of Apache Web Server, or maybe anything, like any startup you join, you will have to read the source code. I have people, like a story, it's a tangent, sorry, but we'll still. So I have a friend. At some point, he rose high up in that company. He was a PhD student here. The reason he rose high up and became a BIP or something of some engineering is because he's the only person who understands the source code of this software product which they ship. And he is not afraid of essentially commit to this code base, because people do like stage small commits, but no one really takes responsibility to say, okay, I kind of can reason about the source code and I can make sure that this commit will not break the software, right? So, and this is the level you like, that's why you're sitting here. That's why the education, the goal is to read the source code and understand it fully, right? Any questions? Not. Okay, good. Kernel map. So not super hard, not super easy, like a little unusual. But again, my challenge here is to teach you to read the source code. So now we're diving into this loop, and for each of those regions, we're gonna just map one of them. So this map pages is the core function which we're looking at. So let's take a look. So again, nothing super surprising, but the notation is a little bit unusual. So let me just move this up. I wanted to move it. Again, page table is passed as an argument. This is the start virtual address. This is the size. This is the start physical address, and this is permission, right? And literally, we're going to do what we were just discussing, going page by page in virtual and physical memory in a lockstep, allocating leaves as we need them, right? So we're careful here, and we say, okay, we'll take this virtual address and we will round it up, or actually round it down to a page, because if you say this address has to be mapped, then the whole page has to be mapped, right? We're careful enough to pass an address which starts on a page, but still we round it down. And the same for the last address, right? Virtual address plus size minus 1. Okay, that makes sense. Now we say, look, we remember this is the page table directory, page dir. We want to first understand if this entry is present or not. Or in fact, we want to understand this is our PTE, right? This is what we want to return here, right? This entry. We invoke a helper function, walk page directory, passing address as an argument, and this one is a flag, which is actually a bad style. I would prefer a flag to have a name, not just one. But the flag tells us if this leaf page is not allocated, please allocate it as needed, right? But this is kind of okay. So you say, look, our goal is to get this entry, page table entry, because our end goal is to update it with the physical address plus flags, but we have this page table directory and an address, so we have a virtual address. So this walk page table directory function just splits this address into 10, 10, and 12, looks up the entry in the page table directory, says, okay, are you present? If you're present, then look up the next 10 bits and return the address of this PTE. If you're not present, please allocate a leaf, and then again, return an entry of a PTE here, address of a PTE here, right? Okay, let's take a look at how it works. So if we are lucky and this page table directory returns us a page table entry, right? If it's not present, we're going to panic. But if it's present, what we do is just write. So this is a physical address, permissions, and the present bit. This is not surprising. This is exactly what we wanted to do, right? Agree? So, and this is what you're going to do in the homework. Who can tell me what the star is? Question about C. Dereference. So what does it mean in human terms, lame?
We're saying the value instead of the address.
Correct. So look, yeah. So you have this table. The table has an entry. This PTE is a pointer, so it's an address of this entry, right? If you want to write this, if you simply assign PTE with value 0x55, PTE will start pointing to 0x55 address, right? That's not what you want to do in C, right? So you say, I will use this star, which means that you dereference the pointer, and this assignment will be actually done with respect to this memory under this address, right? Just a tiny detail, because I know that people don't know C very well. And C++ is so abstract this day that you might not even use a pointer or dereference a pointer. Okay, good. Okay, cool. So that seems easy. Then you say, like, we did this assignment, really. So corresponds to this figure. So that's the end goal. And now let's say, and then what we're going to do after that is just you increment the virtual address and increment the physical address. And if suddenly you're on the last address, you just kind of break out of this loop, right? So the loop is relatively easy, right? So that's how you construct a page table. So let's now take a look at this helper function, which is walk page directory, right? Which did this heavy lifting of locating this page table entry, this pointer, right? Okay, so we kind of know what it should look like, right? So it takes a virtual address, we'll split it into 10 and 12 bits, and it will return a page, like if this is your page table directory, you first have a pointer here going to a leaf, and it returns a pointer to this entry, right? So the specific location in memory is what this function returns, right? So if I ask you how to build this function, what will be inside? What will the code look like? who can guess?
We have to know how many pieces these are allocated, so you know where to allocate the next one.
Kind of, yes. You say, like, if this is your virtual address, you first take a look at these 10 bits. You check this entry in the page table directory, right? And check whether it's present or not, right? If it's present, you follow this address, right? You land, this address will give you beginning of this page, right? And then you take these 10 bits, locate an entry, and just return a pointer to this entry, right? If this one is not present, you say, well, allocate me this leaf, right? And then you back to your algorithm, right? That's kind of the overview of this code. Easy? Let's take a look for a second. Okay, so I mean, I'm just again highlighting this PTE, which we're trying to return. And okay, our first step, take the virtual address, which Intel calls linear address. Take this 10 bits, go into the page table directory, and check if this entry has the present bit set or not. Let's take a look how we do that. So we say we will treat the page table directory as an array. And we'll say we take the virtual address and we will use a helping macro, PDX, which will return this top 10 bits, right? So let's take a look at what PDX is doing. So if your address is split in 10, 10, and 12 bits, PDX is not surprisingly, it's just a shift, right? It's a shift by PDX shift bytes, so by 22 bytes. This is not necessary bug in the code, and I just left it there, right? Agree? Simple macro. This is how, I mean, I understand that some people might not be very familiar with C macros, but again, macros are kind of similar in most languages. So it's like you define a macro PDX, which takes an argument, and this is what happens to an argument. And it compiler literally expands this PDX VA into this source line, right? So in C, macros are not hygienic. So just whatever this expand results in, you will have to deal with. Okay, and then the second helping macro is PTX, actually, right? So those 10 bits in the middle. So this you shift by PTX shift by 12, right? And here you really need this mask because you have to get rid of those bits, right? Because if you shift, you still have them, right? So that's why you're just masking the lowest 10 with this 3FF, right? Agree? Okay, so far so good, so not too bad. Okay, so when we get this, when we work with this macro, we land on this entry, right? So we literally just got this entry. This is where we have this PD, right, pointing to. Agree? And what we do here is, again, we simply say, well, let's check for the present bit. We again use this star here to essentially say, we know that PD is a pointer, so let's take a look at the value under that pointer. That's why we use the star to dereference the pointer, right? And here we have two options, right? So if it's present, this condition is true, you just simply say, I'm going to grab the next level of a page table, right? So this is present. So we'll grab this pointer, right? And let's take a look how we grab it. So you say, we will convert this. We have a helping macro saying convert PTE entry to an address, right? So it's essentially just dropping the lowest 12 flags, right? Because bits of flags, because we don't need them, right? And essentially, here's a little bit of a trick here, because you say, I know that this will return a physical page number, and we want to convert it back from physical to virtual so we can access it through a pointer. So we use another helper macros, P2V, which essentially adds 2 gigabytes to this address, to this number, right? And then you have a pointer which you can actually dereference, right? Because it's a virtual address at this point. Agree? Is that clear? It's just jumping between virtual and physical is a little bit confusing, but like, again, not super hard. Okay, so if you're lucky, right? If you're lucky, those 20 bits of physical address, physical page number, you convert them with this macro. Like essentially we say convert from 20 bits of physical page number to physical address. This is trivial, right? So just adding, zeroing all the flags and convert from physical address to a virtual address. And this is P2V, right? And remember this P2V, this PTE address is trivial, we just discussed it. And P2V is a little bit tricky, but by the way we constructed the address space, we know that if we have a physical address, for example, of this page, the way we mapped everything is we added 2 GBs, right? So it's all mapped with a shift. And that's why you're lucky and you have to, you just say, okay, by converting by plus 2 GBs will, or minus 2 GBs will convert between those addresses. It only works for this region because only this region is mapped with this 2 GB shift. A good question is what happens to this region? It's not mapped with a shift. It's kind of a screw up. I mean, if you are unlucky and you really have to develop a device driver and you have to convert between this physical and virtual addresses, landing here at the very top of your address space here, then you have to do something else. Not the best design choice in x86, I think. But maybe they never touch this region. Maybe they do. We can check it later. But for this region, this math works. Just for this region, from the beginning of memory to fist stop, right? Like technically speaking, from here to here. Okay, so we have this macro, and this is how they work. V2P, virtual to physical, subtracts 2 GBs, and physical to virtual adds 2 GBs, right? Again, they're defined at those lines. And current base is defined as my favorite address 8000 and 0000, right? This is 2 GBs, right? So it has to be familiar to you. Magic. Okay, cool. So we got this. We understood that what this means. And now, since our goal is to simply return the pointer to an entry in the page table, right? So the way it looks is we really want a pointer to this entry. So we have a pointer to here, which is page table. I guess, what is it called in the source code? PG tab, page table. Okay, that's how they call it, page table, right? So this is a pointer here, and we say, but we want a pointer here. So we treat this as an array. We get the entry in this array and just say, let's dereference, let's not dereference, but take an address of this element. So, right, we use this PTX macro of this virtual address that lands us on an entry. So maybe this is entry number 55. And then we use this ampersand to say, okay, please take an address of this element, right? This is how C equals give me an address, right? Is that clear? Good, okay.
That was the PTX macro again?
PTX, PDX, remember, if we have an address which is split in 10 and 10, so page directory index gives you this number, and page table index gives you this number. So it just gives you this middle 10 bits. That's why it's an entry in this. Like we just say, okay, this is the position, right? And this array. Clear? Okay. Okay. And we're returned. At this point, we're done. Like our helping function is done. Right. Good. And if we suddenly were not lucky here, and we say this present bit was not set, we do exactly what we have to do. We say, okay, if this flag, which is an allocation flag, if it's set, if it's not set, then you say return. Or if you fail to allocate, so essentially you say, if you try to allocate a new page table, like this page for the page table leaf, and if you fail, then you will return with a 0, right? But if you don't fail, you say memset, and then do something to this page. I skip a couple of entries, probably don't remember what's going on here. But at this point, what you have to do is you need to make a connection. You have to connect the root and a leaf, right? So how you connect them is specifically you allocated this leaf. So in order to connect, you have to put this entry to point exactly to the leaf, right? And remember, it's 20 bits. It's a physical page number. So you allocator gave you a virtual address of this page. So you will have to convert it. So doing like virtual to physical of this virtual address and get this physical page number and then actually like make sure that the lowest bits are 0. It's true that they're 0 because everything is page aligned in our case. So you just have to essentially write it here, right? And this is what you're doing here. The allocator gave you this page table pointer. You do a virtual to physical page number conversion. You set the present bit, writable bit, and user accessible bit. And this user accessible, I never explain it, and it's a little bit odd here because you say, I allow this translation to be performed, to succeed even from the privilege level user, which is a little bit odd because maybe you're mapping a kernel page. But don't worry, like if it's a kernel page, we're not gonna set this flag in the next level of translation, right? So that's fine. Actually, okay, forget about this flag for a sec. So maybe like it's too much for now. So just writable and present, right? And you just literally fill in this entry. So in terms of my figure, you fill in this one, right? Or in terms of my, yeah, I don't have the other figure. So you just filled in this one, right? And again, if you succeeded, then you have the there must be some connection between this. Okay, then if you succeeded, then you go into this page tab, which are located here, and return an element in this entry, right? Okay, good. So this is how you can start the page table. My suggestion, so if you're working on a homework, so read through the source line and just do something similar. You don't have to write those functions like crazy. You can simplify them, but the core logic and the core syntax of how to construct a page table will be available from those functions. And the source lines in the PDF are exactly those source lines. If you're using an IDE, just look for those definitions of those functions and you will be done. Okay, good. So we have this helper function walk page directory. Let's go back to this map pages function, right? So this is where we invoke this walk page directory. And we kind of already believed upfront that if we have this function, then everything else is fine. We just update the page entry with the physical address of the page, permissions, and a present bit, right? So this is what we are doing this exactly here. We already discussed it. Then we go to the next page by incrementing each address virtual and physical by the page size, right? When we're done with that loop, remember, map pages was called in a loop. When we're done, we get the new page table. It's ready for us to use. So we're going to call this switch kernel virtual memory function, which will literally what it will do is it will take this address, convert it from virtual to physical, and load it into the CR3 register. And like this one will use bits of assembly, which we can guess, so kind of load the CR3 register into EAX, or even like you don't have to do that, just load this value into the CR3 register. And that's it, right? At this point, the hardware will switch to a new page table. This reload of the CR3 register actually flushes all the TLB entries by default, all of them, which means that you invalidate all the previous translation entries and start running clean on a new one, right? So it's expensive operation because the hardware will flush the TLB cache, right? So every time you reload the CR3, you pay the price, right? On modern hardware, there's a little bit of a trickery, and you can switch between page tables by preserving entries in the TLB, but there will be something what is called an address space identifier or a page table tag. And if you say, okay, tag changes, then you just switch between the tags, and the entries don't have to be flushed. They just become inactive in a cache. Just a game, maybe a little bit too much, but we will come back to it. x86 doesn't do anything like that, though. Okay, so what did we achieve? We started on Tuesday. It was a long walk, right? So we started by building a kernel memory allocator. We built it, and we built a page table, which actually is usable by the kernel. So we can now, we got rid of this entry page table directory. This new page table uses 4 kilobyte pages, and we are well positioned to start creating new processes, right? So our goal, remember, from Tuesday was to get to the point when we can create a new process. However, to create a new process, you still need to understand how system call system calls are implemented, right? Because the way you create a process is that, I mean, chicken and egg. So there is a trickery how you create a first process, but then eventually when you create a new one, you do an exact system call. And it's a little bit, it's easier to explain by first looking at how system calls are implemented and then essentially explaining what's inside the exec, right? And I think I explained exec, and then fork is similar, right? So we will take a look at system calls next time. However, since I still have 5 minutes, let's take a look again at what's like bits of initializations which are kind of important, right? So we covered right now these 2 lines, right? So this constructed a kernel memory allocator, donating the pages from the end address to the 4th megabyte, right? This constructed a page table. This will detect other physical CPUs. I might come back to it if I have time. It's interesting how the system detects other CPUs, because right now we're booting on one CPU. Others are sitting idle, and we'll see how they essentially get initialized. So those guys are initializing interrupt controllers, stuff like that, different parts of the IO initialization that actually has a comment for each of them, so you can take a look. What I wanted to cover today in this 5 minutes, which I have, is this seg init function. So it initializes a GDT. Remember, right now, we're still using the GDT, which the bootloader set up for us, right? So we don't really know, I mean, we kind of trust the bootloader to do something good, but it's nice to have something like concrete within the kernel, right? So like, and that's why we say, okay, let's quickly initialize the GDT. So here we say that we will have an array of physical CPUs, and each CPU will have its own GDT, right? So, and we can now learn with this function CPU ID, we can actually read the physical number of a CPU which we're running on. It can be 0, the boot CPU, can be 1, the second CPU, or maybe the third one, and so on, right? On each of these CPUs, like it just array of CPUs, we get one CPU. Each CPU will have its own GDT, right? Let's take a look at how it's allocated. So this is the CPU struct. It will become important and clear later. This is the current running process. This is the context of the scheduler to context switch and pick the next process. We will explain it later. What's important here is this GDT. So each CPU will have its own GDT. It will become clear why we need a GDT on a different CPU, because we'll be running different processes on each CPU. The GDTs will be slightly different, right? But we get them, and this is the GDT, and we only define some number of entries. It's not a big GDT, maybe 5 entries. Each entry, remember, it was when we used the bootloader, we used like a very cute macro, which just says base address, size, and some flags. Those macros were abstracting this data structure underneath, because for historical reasons, the bits of the base and the segment are split all over the place, right? So for example, bits, so base address bits 0 to 15 are stored here. 16 to 23 are stored here, and 24 to 31 are stored here. A little awkward, right? Like backward compatibility reasons, like that again. So the limit itself, 15 bits stored here. Those are the different flags, right? So a lot of like bit manipulations. But again, if you say, okay, I want to define this data structure in C, which actually bit-to-bit maps into this hardware descriptor format, this is the way to do that in C. So C allows you to say, like, this is the 16 bits, this is 16 bits, this is 8 bits, and this data structure will be laid out in memory in such a manner that it maps the physical layout. It's kind of important. So it's, I think, I forget what it's called, but not every language allows you to define a data structure for which you can define a specific bit layout, right? So sometimes languages are free to like flip those fields, do the various optimizations, right? But in C, you can do it. Okay, so this is one segment descriptor, one element of this GDT array. GDT is just a table, but these entries in this array are just funky. They have this format, unfortunately, but fine, who cares? Like, as long as we can define them, we're good, right? And this is what I wanted to cover. So next time, we will switch the gears a little bit, and I will explain how interrupts work. But and there we will start building first processes. Okay, thank you. So we'll see you then next week. There will be a quiz this Friday, and the homework hopefully today.